I believe we are recording. I hope so. Yeah, I will just have faith that we are recording. Anyway, howdy all, and welcome back to the AST-103 lecture series of spring 2022. This is lecture 3, Thinking Like an Astronomer. Effectively, what I'm going to be going over today is the process of science. What are the steps, or what are the essentially what is the broad procedure that scientists go through in order to be assured of that what they are doing is rigorous and accurate. But before I begin, I wanted to kind of revisit a couple of things from previous lecture. Last lecture I talked about the scale of the solar system, and so I may have mentioned, either in that lecture or in class, that there were a group of young men who created a scale model of the solar system in the Nevada desert. And I am providing the YouTube link here. I highly recommend checking it out. It really does put into perspective the relative sizes and distances of the various objects in the solar system. And commensurately, I'm going to be revisiting this when I talk about the discovery of exoplanets, and you really get a better feel of just how extraordinary it is to find exoplanets using the transit method, where the light from the star is depleted due to the fact that the planet is blocking some of that light. The geometry that has to take place in order for that to work is fairly astounding, again, considering the scale of things. The other thing I would like to do is, I guess, Hawk Eleanor Lutz. She is at this point, at the time that I bought this, she was a biology PhD student. She may have already graduated by this point. But what she has done is created art which is data-driven. And she does this across multi-fields. She's including astronomy. This, for example, is a piece of art that she has done by looking at the orbital, basically the orbits of all of the objects within our solar system as it was known at the time. And so again, this gives you another sense of essentially how crowded the universe is, or how rarefied it is in certain regions. So in the inner part of the solar system, out to about Earth, there really aren't a lot of objects orbiting around the sun, primarily just the planets. But when you go from Earth through Mars out to Jupiter, you see that we have a tremendous amount of stuff. I mean, it's not quite Empire Strikes Back, dense asteroid field, but we're talking about millions upon millions of small asteroids, comets, and so forth that are within the inner part of the solar system. So, in one sense, the universe is far more far more populated, or has a far larger population than is canonically believed or canonically shown in pictures of the solar system and so forth. We always concentrate on the planets. We rarely give thought to the, like I said, millions of asteroids and comets that reside in our solar system. So yes, I highly recommend checking out Ms. or Dr. Lutz's work. Like I said, she does art, data-driven art across multi-disciplines. So, I would like to start off this lecture by quoting the late, great Albert Einstein. All knowledge of reality starts with experience and ends with it. Propositions arrived at by purely logical means are completely empty as regards reality. Because Galileo saw this, and particularly because he drummed it into the scientific world, he is the father of modern physics, indeed of modern science altogether. Really at the core of this, what this is addressing is really the Copernican revolution. Prior to Copernicus and Galileo and Newton and so forth, the way that science was done, or more accurately describe natural philosophy is through, and I know I'm going to get this backwards, is through deductive reasoning, basically a top-down perspective. First, you make a grand argument about how the universe is or how it should operate, and then you tailor your arguments, or you tailor your explanations for specific events based on that overarching idea. This was something that Aristotle was very much known for. But in science, particularly modern science, and what Galileo was really the pioneer was, assuming I got this, I'm correct about this, inductive reasoning, where you start off small. You take small experiments, and you determine the results of those experiments, and then you piece together all of those experiments, the results of all those experiments, to see if there are any commonalities or any trends within those experiments that will lead you to larger truths. And so you build the overall overarching theory of how the universe is by looking at individual smaller experiments and basically tying all of those together. Now, one of the questions I think is becoming even more relevant today, particularly in my experience, there seems to be a rise in science denialism, particularly in this day and age of COVID, mask wearing, and so forth, and vaccines and so forth. So I think it's more crucial than ever to understand the difference between science and non-science or pseudoscience. Defining science is actually surprisingly difficult. If we simply look at the derivation of the word, and I'm going to mispronounce this, scientia, it's on the screen. It's Latin for knowledge. Now, that is exceedingly vague, because because I would not be so arrogant as to say that astronomy is the end-all, be-all of knowledge. Certainly not science, all of science being the end-all, be-all of knowledge. We have artistic knowledge, we have emotional knowledge, we have spiritual knowledge. All of these are various forms of knowledge. But there is only one specific sort of criteria that distinguishes science from all of the rest. But before we get into those distinctions, what I'd like to do is I'd like to define terms, because I think any conversation concerning science, what it is, what it isn't, we all have to have a basic vocabulary from which to agree on and move forward for. So the definitions I'm going to talk about are fact, hypothesis, law, and theory. Now, a fact is a result of an observation or measurement. I am 1.8 meters tall. That is a fact. It doesn't matter if I measure that. It doesn't matter if you measure it. It doesn't matter if an alien from Alpha Centauri measures it. Given a set unit of measure, like a meter, I will always be 1.8 meters, regardless of who measures it. The Earth being round is an observable fact, because now we have satellites in orbit that can take actual photographs of the entirety of the Earth, and we can see that it is a sphere. Next is a hypothesis. Essentially, a hypothesis is a guess. More specifically, it's an educated guess. It is, and what's most crucial about a hypothesis is that it must lead to a testable prediction. So you must come up with an idea of how the universe operates and be able to test that idea if it is to be a valid hypothesis. That is not to say the idea itself is not valid if you can't test it. It's just not technically what I would consider to be science. There's a lot of great ideas, a lot of great hypotheses, that things like string theory, M theory, all of these put together, but unfortunately we do not have the capacity to actually test these ideas. So when we talk about science, or at least when I'm talking about science here and moving forward, a hypothesis must be testable. A law is an explanation, usually in terms of mathematics, that describes a certain natural phenomenon. For instance, Boyle's law or Ohm's law. In a way, the gravitational Newton's universal law of gravitation, although that becomes problematic as we move on and increase our understanding of relativity as opposed to classical mechanics. But at the heart of it, a scientific law is something that addresses a singular phenomenon within science. Next, we come to perhaps the most misused term among common parlance, and that is a theory. Now, according to dictionary.com, and I am typically not one to use the dictionary as a meaningful source for anything, but for this, it illustrates quite nicely. Let's start off with the sixth definition of theory. The sixth definition is a contemplation or a speculation. This is what's typically thought of as the meaning of a theory in everyday life. When you say, I have a theory, this is basically the meaning behind it. The example I provide is, I believe that Jeffrey Epstein was killed by the Clintons, or I have a theory that Jeffrey Epstein was killed by the Clintons. This is not something that can, one, it's a rather singular event, or it deals with a singular topic, and two, it's not very testable. Scientists actually use the first definition in the dictionary.com, and that is a coherent group of tested general propositions, commonly regarded as correct, that can be used as principles of explanation and prediction for a class of phenomenon. Example is Einstein's theory of relativity. Einstein's theory of relativity is an overarching umbrella of essentially how things move in the presence of gravitational fields and how things move relative to each other. So it details many different phenomena, from collisions to simple straight motion to effects of gravity on various bodies. It deals with a large volume of phenomenon. And along with that, all of the predictions made by the theory, Einstein's theory, have been proven to be true. There has yet to be an explanation, or there's yet to be an experiment which has falsified Einstein's theory of relativity. Now, this is a very key distinction to make. There is a difference between falsification of a theory and a theory being incomplete. Einstein's theory of relativity has not been falsified, but in certain areas, it's proving to be incomplete. And what I mean by that is that there are certain phenomenon where we can't, that Einstein's theory of relativity simply can't explain. Right now, we are undergoing, I hate to use the word crisis, but we are undergoing a revolution, as it were, in terms of trying to reconcile Einstein's theory of relativity with quantum mechanics. It's becoming very difficult to actually do that. But that is not to say that Einstein's theory is falsified or wrong. It just means that it's incomplete. Scientific theories are constantly being tested and revised. When an experiment comes to the forefront that illustrates that the current understanding of a particular phenomenon or a group of phenomenon is wrong, then there are two outcomes. I can't find the words. There are two modes from which you can operate. You can either reject the theory entirely when you realize that the fundamental nature of the theory is inaccurate, such as with regards to the theory of relativity and classical mechanics, or you can revise it. Basically keep the core idea of the theory, but just change it such that it now incorporates the data from the new experiment. For example, the Nice theory of planetary formation was simply based on a single data point up until roughly around the mid-90s, that single data point being the solar system. And it did a very excellent job of describing or predicting the motions of objects within our solar system. But then we started finding exoplanets in places that the NICE model couldn't explain. Jupiter's really close into the sun, worlds that pretty much are covered in giant oceans. And so we had to revise that theory. We had to revise our theory or understanding of solar system formation to include these unexpected results. Another point, and I want to make this very clear, is that nothing in science is proven. Science is provisional. If someone tells you that something in science has been proved, they're either lying or they're trying to sell you something, or they're confusing proved with fact. A scientific theory can never be proven. It can state with confidence, this is how the universe behaves, but it must always keep an open mind that to the possibility that new data and a new experimental experience could in fact cause that theory to change or be rejected entirely. All right, hopefully we're back on track now. When defining what science is, or describing the process via which science is done, there are certain hallmarks that I basically point to, or certain signposts that guide me in my understanding of science. And so I'm going to go over each of the 5. The first one is that science is an exploration. Now, in most scientific fields, these are conducted through controlled experiments, where you are looking at a set of variables and you control what those variables are. You set basically you set those variables to be a certain value, and then see how another variable is affected by the experiment itself. Chemistry is a great example of this. Physics is also a great example of this. But there are certain fields of study that cannot work this way. Astronomy being the most applicable, in that in astronomy we cannot physically manipulate that which we are observing. We cannot put Jupiter in a lab to determine how large it is or how much it weighs. So we have to basically observe what the universe has to offer and then make inferences based on those observations. And such as we can use, for example, the orbit of planet or orbit of moons going around Jupiter to determine the mass of Jupiter based on our understanding of gravity. So astronomy is an observational science. So the experiments, as it were, often deal with how you plan your observations and then ultimately how you analyze the data. An example of an astronomical experiment would, again, going back to the theory of relativity, is or the first basic proof, or excuse me, not proof, the first basic piece of evidence to support it. And that was the solar eclipse of 1919, and the observations were performed by Arthur Eddington on an island west of Africa. Ultimately, what the experiment, or what the observation showed, was that Einstein predicted that the apparent distance of stars would be larger in the presence of a massive body, in this case the sun, and that is what Eddington's observations proved. He measured the distances between the stars when the sun wasn't present, and then when the sun was present in eclipse, and he noticed that, or he was able to measure that the stars appeared to be farther away from each other with the presence of the sun. With Hallmark 2, this is in regards to the science versus religion sort of debate. Science is only interested in understanding physical reality. Basically, when scientists determine, or when scientists pose hypotheses as to how things operate, or how things should operate, we always look for physical mechanisms. We never default to divine inspiration or divine intervention. We never default down to, well, God did it. We always look for a physical mechanism behind why things appear to do what they do in the universe. We also, as my father would like to, my father was commonly known to tell me, is we use the sort of the KISS approach, or keep it simple, stupid. When we are dealing with a particular phenomenon, let's say let's say where the Earth is located in the universe. Is it geocentric or is it heliocentric? Is the Earth the center of the universe, or is the Sun the center of the universe? We had gotten to a point where our predictions of where planets would be were the same ultimately, or the same essentially, if you use a geocentric model and whether or not you used a heliocentric model. Both models produced the same predictions with the same precision. So the question is then asked, which one do you use? And so Occam's razor, which I'm never going to find out what exactly a razor is, but Occam's razor essentially states, if two hypotheses explain all observations equally well, then we should use the one that requires the fewest assumptions. Basically, you want to use the simpler model. In this case, I use the word model and hypotheses interchangeably because in actual practice, your model is your hypothesis. A geocentric model is the hypothesis that everything is orbiting around the Earth. A heliocentric model is everything is revolving around the Sun. As it turned out, when you look at the two models, the Ptolemaic model versus, say, the Copernican model, Copernican model is way easier to use than the Ptolemaic model. And so, by Occam's razor, the one that is more than likely correct is the Copernican model, and then it was later shown by observations, more detailed observations by Tycho Brahe and the modeling of Kepler, that the heliocentric model was in fact correct. It basically broke that Occam's razor conundrum. But Occam's razor, again, if you are confronted with two explanations for a phenomenon, and both explanations seem to work equally well, you take the one that is simpler in process than the other one. I've already sort of emphasized this, but I'll emphasize it again because it needs to be emphasized. A scientific hypothesis must lead to testable predictions. If your idea does not lead to a quantifiable prediction, such as if I put a certain amount of salt into a beaker containing an egg, that will move that egg a certain distance. Unless you can do that, then that is not a scientific hypothesis. A scientific hypothesis must lead to quantitative results, or quantitative testable predictions. So, and in this way, science is continually asking the question why. We are never settled, or we are never satisfied with basically what is. We're constantly trying to figure out the specifics of why certain phenomena are the way they are. And so, when we use these hypotheses and we test them, then we move forward. We have to either revise a hypothesis or abandon the hypothesis, or accept the hypothesis based on those results. And I'll get into that a little bit more specific in a second. And then hallmark 5, and really this is more of a hallmark of astronomy rather than science in general, is what is known as the cosmological principle. It is a updated version of the Copernican principle, which basically says that we're not special. The cosmological principle has two major parts to it. First one is there is nothing special about our place in the universe, meaning that if you were to take observations of the universe from our position, and then if you were going to take observations of the universe from, say, Alpha Centauri or somewhere in the Andromeda Galaxy, those observations would essentially be the same. Ultimately, the conclusions that you would come to based on those observations would be the same. Sorry about the phone. Probably not important. Anyway, where was I with that? So what it means is that the universe looks the same no matter where you are in that universe. One sort of consequence of that is that there is no center to the universe. Everywhere is a center, depending on how you want to perceive things. But there is no point from which the universe sprang into being. The second caveat is that, and this is vital to our understanding of astronomy. If this weren't the case, then astronomy would pretty much be dead in the water. And that idea is that all physical processes that we know of on the Earth operate the same way in every part of the universe and every time in the universe. So the example I like to give is if you drop Mentos into Diet Coke, it's going to explode. If you're on Jupiter and drop, let's say Europa, because you can stand there. If you drop Mentos into a Diet Coke, it's going to explode. If you do it in the Andromeda Galaxy, you got it, it'll explode. The reason why this is vital is because we make observations of the universe at various times and various locations. And if this did not hold true, if we could not with confidence say that Mentos exploded in Diet Coke everywhere, then we really couldn't confidently make any conclusions as to how stars are formed in other galaxies, how other galaxies are formed, and so our whole endeavor pretty much falls apart if we cannot make this one, if we do not make this one clear assumption. And really, at this point, there is no evidence to suggest that this assumption is incorrect. So how does science work? Again, this is a very rudimentary outline of how science works. Depending on your field of study and depending on the experiment that you're doing, the specifics of this can vary quite significantly. But in rough estimation, or first order approximation, as it were, this is referred to as a scientific method. It starts with asking a simple question, or making a simple observation. The sun rises in the east and sets in the west. You then do some background research. You try to find out, is this always the case? Has it been doing this since people have been observing the sun? You also look up more specific information, like, does it always rise precisely due east, or does that position in the east change? And conversely, does it change when it goes to the western horizon? So you want to learn as much as you can about the underlying subject to better inform how you're going to answer your question. And the way that you're going to answer your question is by constructing a testable hypothesis. So to follow up with that example, you might say that the reason why the sun rises in the east and sets in the west and does so at various points along those horizons is that the Earth is rotating and is tilted on its axis. And so you would then create a set of observations or an experiment in order to test that hypothesis. Is it true that the Earth is rotating underneath the sun and is tilted on its axis? And you would then conduct said experiment or set of observations, and you would see whether or not the results of those actually matched up with your prediction. So, to be even more specific, your hypothesis could be that the Earth's axial tilt is 23.5 degrees. If your results say, yes, it is tilted, but it's tilted at 60 degrees, then you would have to go back and you'd have to revise your hypothesis. You'd have to say, all right, well, why is, or I believe that the Earth is revolving underneath, or rotating underneath the sun, and it is tilted at 60 degrees. Or if your observations do not prove or do not show that the Earth is rotating at all, then you have to basically abandon that hypothesis and come up with a new one, which is testable. As I said, science is a process. You go through this process over and over and over again. We do not, as I said, we do not stop, as scientists, we do not stop asking the question why. To give that continue that bad analogy, once we figure out that the Earth is rotating underneath the sun and is tilted at a certain angle, next question is why? Why does it rotate at all? Why is it tilted on its axis? And so we gather more information about that particular subject. We then form a hypothesis. We test that hypothesis, and then we basically move on from there. So it is an ongoing process, and for the most part, that ongoing process serves the purpose of verifying or refining the current understanding. So, for example, the theory of relativity, a lot of the experiments that are out there now are in the pursuit of refining Einstein's predictions, or refining our understanding of theory of relativity, so we can use it with more accuracy or better precision in other areas. But that's not always the case. Sometimes science is revolutionary. Sometimes certain observations or certain experiments simply cannot be explained via the framework that has been established. And I'll get into more of that later on. But what I want to do is I want to start off by looking at the more traditional case of science, particularly in astronomy. This is the TRAPPIST-1 system. It is my favorite exoplanetary system. So first you want to start off with, well, speculations. You want to ask a question. And there were two fairly famous gentlemen who posed a certain question as to whether or not the Earth was singular in the universe, or probably more specific, whether or not our solar system was singular in the universe. First one was by the name of a gentleman by the name of Giordano Bruno in around 1600, and he said, quote, "This space we declare to be infinite. In it are an infinity of worlds of the same kind as our own." Now, as an aside, Bruno has been held up by some as a martyr to science because he was burned at the stake by the church. And it is true that his belief in exoplanets was a reason for it, but it was certainly not the major reason. Major reason was that he refuted the divinity of Jesus, which was probably a more important consideration to the church than exoplanets. But, like I said, I digress. Now we move to Isaac Newton in 1713. And he says, quote, "And if the fixed stars are the centers of similar systems, they will all be constructed according to a similar design and subject to the dominion of one." In this case, what he's talking about, one, and really in both cases, what they were discussing is basically God. The crux of the argument is, and this actually goes back to the cosmological principle, the crux of the argument is, if we have a solar system here, and the universe is infinite in size, if creation is infinite, then what is to stop this that we see around us, our solar system, from being replicated around other stars? Why is it that it would be more improbable or harder to believe that we are unique in the universe if the same physical laws applied everywhere? If one star creates a solar system, then another star should also be expected to create a solar system, unless there is a viable reason that it doesn't. Now, back in the 1700s, these were pretty much pie-in-the-sky ideas. They essentially could not be led, these questions could not lead to testable hypotheses, because there would be no way to test them. That changed around 1952 with a gentleman by the name of Otto Struve, and he proposed a rather ingenious method called Doppler spectroscopy. Now, I've already discussed in the first lecture what the Doppler effect is, and essentially what that means is that if a luminous object is moving towards you, the light of that object becomes bluer. If a luminous object is moving away from you, the light from that object gets redder. So, as you can see in the diagram, what we have is that in a true planetary system, the star is not fixed. Both the planet and the star orbit around a common center of mass. And so the star will actually wobble as the gravitational influence of the planet goes around it. This method does not directly observe the planet. What this method does is it observes the blue shift and red shift of the star as it wobbles in the presence of the gravitational influence of a planet, in the presence of a planet due to its gravitational influence. Unfortunately, at the time, these measurements require a very high level of precision. This was not possible in the 1950s. This barely became possible starting around the late 1980s and then into the 1990s. And we are now getting to the point that we can do this with fair regularity, but there are still limitations to what we can find using this particular method. And I'll go more into exoplanets and their detection methods and their limitations later on in the semester. But the main takeaway point here is that in 1952, the first method for detecting an exoplanet was postulated. And so now we can move forward and actually create testable hypotheses. But as with all scientific endeavors, you're going to have missteps. You're going to have times when the observations appear to confirm your hypothesis, but in fact, upon closer study, they don't. Now, one of the aspects of astronomy that I haven't mentioned so far is repeatability. An experiment must be repeatable, meaning that if I do an experiment, I drop Mentos and Diet Coke, it's going to explode. If you construct the same experiment with the same Mentos, the same bottle, same Diet Coke, whole nine, if you replicate my exact experiment, you will get the exact same results. Someone in Alpha Centauri does the same thing. Then they get the exact same results. Your observations or the results of your experiment must be able to be found via other teams or other researchers. The first false claim of an exoplanet was made by Jacob and C. back, I want to say back in the 60s, although I could be wrong about that. And what they looked at was the binary system 70 Ophiuchi. They saw two stars orbiting around a common center of mass. This is a common occurrence in the universe. Roughly half the stars in the universe are in binaries or multiple systems. But what was unusual is that if you have these two stars, ordinarily the motions of those two stars is highly predictable. It's very well understood how those how those stars are going to orbit around each other. So it's very easy to find orbital abnormalities, or when the orbits don't actually match up to the expected results. And so what Jacob and C did was they went through and they discussed various possibilities as to why these these anomalies took place. And one of those was the hypothesis of a dark planetary body. So the idea here is that there is a third gravitational source in the system which is causing the other two objects to move in ways that wouldn't be predicted, or wouldn't be, move in ways you wouldn't expect for just two bodies. The problem with this is a mathematician by the name of Moulton came by and said, all right, well, if that's the case, then what I can do is I can create a simulation where I'm going to put in a mass, I'm going to put in a planet into that system, and I'm going to see how it moves. That's essentially his hypothesis. If I place planet X at this orbit, or if I place planet X in this position with respect to the two stars, can I create the orbital abnormalities that Jacob and C saw? Well, Moulton said no. Actually, if you place any object, any third object into that system, it becomes what is known as dynamically unstable. It basically falls apart. Planets either collide with themselves, or they get blown off, or they fly off into outer space. Now, I have to admit, I did not follow up on what actually is the reason for the orbital abnormalities in 70 Ophiuchi. My suspicion is that there are systematics that they did not take into account. But this is a cautionary tale. Jacob was able to look at Moulton's results and basically say, okay, I have been shown to be wrong. I have been shown that this hypothesis doesn't work. It's not repeatable. C, on the other hand, rejected this idea. C could not accept the fact that he had not found a planet, and he ruined his career by it. Because the evidence against the planetary body was essentially irrefutable by the scientific community, he was blackballed. His career essentially went nowhere after that. Next, we come to the second major famous claim of an exoplanet that wasn't. Peter Van de Kamp, who was a widely respected astronomer, did numerous groundbreaking work in optical astronomy. He used the Lowell Observatory, and he was looking at Barnard's star. Barnard's star is the fastest moving star in the sky, in the sense that if you were to plot its motion or velocity across the sky relative to the rest of the stars, it is faster than any other star. So it's in that it's significant, it's very well studied. Well, Van de Kamp looked at it, and he noticed what was on the left. RA is celestial longitude, declination is celestial latitude. And what he noticed was that the star did not move in a straight line. Newton tells us that it should, unless acted upon by some other body, it should move in a straight line. But because it appears to wobble, the natural explanation is that there must be some other gravitational body in that system. And since you can only see Barnard's star, then it makes sense that a planet would be essentially unseen but still gravitationally affecting it. The problem was that it's not this issue was not repeatable, because again, Van de Kamp was so highly respected that when this claim came out, this extraordinary claim came out, everybody pretty much stopped what they were doing and looked at Barnard's star and to see whether or not they could see what Van de Kamp was seeing. Unfortunately, they couldn't. And so Van de Kamp's claim was essentially thrown to on the trash heap. Sadly, Van de Kamp went the way of C, in the sense that he went to his grave still believing that he had been the first person to discover an exoplanet. But unlike C, he had a very well established career, and people essentially gave him the mulligan on that one. As it turns out, the most likely explanation here is definitively systematics. It's believed that the Lowell telescope, for some reason, there was a vibration within the telescope that caused the apparent shifting of the stars. So next we get to the confirmed detections. The first one, and this is the first confirmed detection, and this one is wild. This was in 1992, and it was detected around the most unlikeliest of objects. It was detected around what we refer to as a pulsar, or the remnants of a dead star, a star that had gone supernova, and the pulsar was the core almost entirely composed of packed-in neutrons that was left behind. No one in their right mind would have expected planets to be around a pulsar, because, well, a supernova is pretty violent, and you'd expect that planets would be destroyed in that event. Now, it's still an open question as to whether or not how these planets actually got there, but because pulsars are such spin with such with such accuracy and precision, they're known as cosmic clocks. And so when that clock is disturbed, when that rotational period appears to change, it has to be due to the gravitational influence of another body. And this was observed by multiple researchers, multiple teams. And so this has, again, been well studied and confirmed. The next confirmed exoplanet around a star similar to the Earth was 51 Pegasi b, and it was discovered and confirmed in 1995 using that Struve Doppler spectroscopy method. But the unusualness of this particular system was that it is now known as a hot Jupiter. It is a planet which has about half the mass of Jupiter, located roughly 10 times closer to the Sun than Mercury is. Again, no one in their right mind expected a Jupiter-sized planet to be that close to its host star. And so there's a lot of fervor as to trying to explain how that happened. And ultimately, that was one of the things that led to the revisement of the Nice theory of solar system formation. Which brings us to Gamma Cephei AB, or Latham's planet. Now, this was discovered in 1989. Unfortunately, it was not confirmed until 2002 because the data was messy. And this was by no fault of David Latham. His observations were as good as he could have made them back with the technology of 1989. It was just that there was so much noise in the data due to various things, mainly the jitter of the star itself. The jitter of the star has certain particular motions which can mask the appearance of the Doppler effect. And the problem was that no one else could reproduce his observations and be able to definitively state that what they were seeing was in fact due to a planet rather than some other astrophysical situation. It was only until 2002 that someone revisited Latham's planet with better equipment, with more precise equipment, and was actually able to confirm that the signal that was initially found was in fact from a planet as opposed to something else. Scientific revolution. As I said, science vulnerability is its greatest strength, in that we have to keep an open mind, and some might think that that's a vulnerability, or the fact that science can't be proven is a vulnerability. But that's where our science's strength comes in that it allows us the opportunity to grow, to grow and to move forward. There have been major overhauls and revolutions. As I said, the Newton's special and general relativities, Newton's special and general relativity replaced Newton's theories, or what we commonly refer to as classical mechanics. That is a major overhaul of science. Another major overhaul was the caloric theory of heat. That was a major overhaul in our understanding of thermodynamics. But there are smaller ones for ideas that can change a specific subfield of a science. Hubble's observation of expanding universe replaced the old paradigm of a static, steady-state universe, or small static universe. It illustrated that the universe was in fact expanding and not just a constant in the universe for all time with the same size and forever. And that revolutionized the field of cosmology, which is a subfield of astronomy. Ultimately, it is nature that decides which ideas are good and which ideas are bad. It is not the scientist's role to make those decisions. We must, in order to, if a scientist is being honest, they have to keep an open mind and basically do what nature tells them to do. Ultimately, what we are looking for are patterns. Patterns are good. Patterns are nice. Patterns make things easy, or at least easier. Because with patterns, we can hopefully determine an underlying mechanism for that pattern. The pattern of certain stars being visible during certain seasons, that tells us that the Earth is revolving around the sun, for example. Now I'm going to end this lecture, which is going a bit long, on this idea of correlation versus causality. Now, in some cases, correlation means correlation and causality are the same. In some cases. For example, or to illustrate this as a point between astronomy and astrology, both astronomy and astrology use this correlation is causality argument in various things. The problem is astronomy is right and astrology is wrong. I will leave it for that. That is a subject for a much longer conversation. But let's get back to astronomy. In this case, in the case of climate change, correlation does lead to causality. In this case, what we're looking at are, over the same time period, we're looking at the global temperature or temperature anomaly. The global temperature anomaly. What that means is basically you take a fiducial point and you refer to that as your 0 point. And then you measure all of the global temperatures off that 0 point. So for example, this 0 point was more than likely around 1930, the late 30s or maybe late 40s. And then you measure all the so what we see is that in the earlier years, the world was cooler, and the later years, the world is hotter. Blue lines equals cold, red lines equals warm. And you notice this global trend, this overall global trend of global warming, from the 1880s to the present epoch. You also can measure the CO2 concentration for the Earth during this same time frame, and we notice that it also increases. And so one of the ways that, or one of the rationales for why we know that this correlation leads to causality is the distinction of 1880. The reason why 1880 was chosen was because the world went through a massive revolution, an industrial revolution. A large section of, or large proportion of our energy needs were no longer being fueled by wood, they were being fueled via coal, which produces a lot more CO2 than wood burning did. And so it makes sense that given our burning of coal and our adding more CO2 into the atmosphere than we previously were, we can see that the consequence of that, with CO2, which is also known as a greenhouse gas, it traps warmth within our atmosphere, that again, as it increases, the world should also increase in temperature. There are other various tools that we use there's more evidence for climate change than simply that. Problem is, you run into those who deny climate change, essentially another subset of science denialism. And one of their favorite things is to perform what we refer to as cherry picking. So they might use this graph, which is essentially the same thing as I was showing you before. It's over a certain range of time, there is a variation of the temperature of the world with respect to, or variation of the temperature of the world and the CO2 concentration. And you can see that the correlation sort of isn't great here, where during certain years, namely between 1980 or so to mid-2000s, there does seem to be a positive correlation, but in the other two time periods, there isn't. The problem for this is there's no physical reason to start this at 1950. There's nothing that happened in 1950 that would have explained a global change in CO2 concentration, unlike the 1880 benchmark or marker, which we can point to the Industrial Revolution as to a cause for why CO2 would have increased significantly at that point. So if you take certain smaller chunks of data out of context, and you choose the ones that best fit your understanding or your worldview, that is referred to as cherry picking. And that goes back to the Aristotelian thought. First, you have an idea of this is how the world should be. The world ain't warming. And then you find evidence to support that conclusion, as opposed to looking at the evidence first and then coming to the conclusion later. But, and this is my favorite example of this, correlation does not always equal causality. So, the sun goes through cycles, specifically sunspots, which are these magnetic features on the sun. They rise and they fall with a certain cycle. If you were to plot, and this is true from the 1960s all the way up to 2000s, I haven't checked to see if it's still valid, but there is a remarkable correlation between the number of sunspots and the number of sitting Republican senators. As the number of sunspots goes up, so too apparently does the number of Republican senators. But hopefully, I would say that, contend that no one in their right mind would believe that either the sun is affecting the minds of the voting populace to vote more Republican, nor do I believe that Republicans are secretly reptilians with the power to affect the internal mechanisms of the sun. The two cannot be physically correlated, or the two cannot be physically tied together. One cannot cause the other. So this is a note of caution that correlation does not always mean causality, but it can. And when you see a correlation between two factors, it behooves you to investigate whether or not there is a physical link that might describe it, or not. All right. I will end this today, and I will get this posted as soon as my computer lets me. And I will bid you adieu. I'm trying to think of what we're going to be covering next week. I believe I will be talking about celestial coordinate systems and the movement of stars in the night sky. All right. Peace out.